Hi folks, we're going to start into stoichiometry today. It's a big, long, scary word, and it involves a lot of math, which is big and scary to a lot of people. But I'm hoping that by explaining it to you in an easy to understand way, it won't be so scary. So let's do a thought exercise first. Here I've got a recipe for some cookies, and let's say I've got 5 eggs, and I just want to make as many cookies as I possibly can with my 5 eggs. I've got plenty of everything else, but eggs are the things that are holding me back. So if I've got 5 eggs, how many dozen cookies can I make of this recipe? Think about it. I think lots of you guys can do this in your head without too much thought. But I want to show you a systematic method that works for any recipe, even a chemistry recipe. And it's going to involve conversion factors. So you may already realize that you can make 2.5 recipes if you've got 5 eggs. And 2.5 recipes would be 2.5 times the 5 dozen cookies. So you would be able to make 12.5 dozen cookies. But we can be more systematic about this because chemistry recipes aren't always as obvious as cooking recipes. So if we've got 5 eggs, I can use this recipe to create a ratio to help me make a conversion factor for doing the problem. I know that 2 eggs results in 5 dozen cookies. So I pick out the parts of the recipe that I need to make this ratio and use it as a conversion factor. 2 eggs makes 5 dozen cookies. I put eggs in the denominator because that way my units cancel out, and I have dozen in the numerator, and I end up with 12.5 dozen cookies. I like to start with familiar examples so that you know ahead of time what the answer should be. Because with the chemistry questions we do, you won't know the answer ahead of time. So I recommend you always start with an example that you understand so that you can apply the technique to a situation that you don't understand as clearly. So what we did was we made a ratio from the recipe, a ratio of eggs to dozens of cookies to make our conversion. When we do stoichiometry, we do the same thing, except the recipe is our balanced chemical equation. Stoichiometry is using quantitative relationships between substances in your balanced chemical reaction, and it's always based on mole ratios, those coefficients that you wrote in the front of the substances in your balanced chemical equation. This mole ratio is going to be a conversion factor that we use in dimensional analysis. It's going to relate the mole amounts of any 2 chemicals that are in that balanced chemical equation. I've already said that it comes from the coefficients of the balanced equation. And this is the only way that you can convert from one substance to another substance in a chemical reaction. So what do these mole ratios look like? What are these conversion factors like? In an equation like the one shown here, magnesium plus oxygen makes magnesium oxide, there are 6 possible mole ratios, 6 possible conversion factors for us to come up with. The first pair of conversion factors help us convert between magnesium and oxygen. Either you can say 2 moles of magnesium for 1 mole of oxygen, or you can say 1 mole of oxygen for 2 moles of magnesium. The next option relates oxygen to magnesium oxide. So these 2 substances in the chemical equation. 1 mole of oxygen is related to 2 moles of magnesium oxide, or 2 moles of magnesium oxide is related to just the 1 mole of oxygen. The last pair of mole ratios relates the magnesium to the magnesium oxide. 2 moles of magnesium result in 2 moles of magnesium oxide, or 2 moles of magnesium oxide come from 2 moles of magnesium. So with these mole ratios, we're just using these coefficients as shown in the balanced chemical equation to create the mole ratios. So how do we actually use these conversion factors in dimensional analysis? Let me give you the steps first. Step 1, you have to start with a balanced chemical equation. If you don't have a balanced chemical equation, your coefficients won't be right, and therefore your ratios won't be right. Then you set up a dimensional analysis problem. We did this, we've been doing these already, but just as a refresher, these are the steps for dimensional analysis. You identify your known and your unknown. You draw the dimensional lines. You insert the correct conversion factor. You check that units cancel, and then you do the math. Remember, the mole ratio is the only way to convert from one substance to another substance in a calculation. So if you're given information about one substance and you're supposed to calculate something about a different substance, that's when you know you have to use a mole ratio. Okay, so this is the process that we use to convert from moles of one substance to moles of another substance. You're going to, in the denominator, you need to divide away the number of moles of the known, the substance that you started with, and you have to bring in the numerator, the number of moles of your unknown. This is the conversion factor you use when your known and your unknown are both in units of moles. So let's do an example. How many moles of potassium chlorate must decompose in order to produce 9 moles of oxygen gas? Well, our known is 9 moles of oxygen. This is my known. And my unknown is moles of potassium chlorate. We need to know what the balanced equation is. That's step 1. And I'm giving you this balanced equation because this is a more complicated decomposition reaction than one that I would ask you to predict products for. We label our unknown and our known so that we can insert the values into the math problem here. Our known is 9 moles of oxygen, and we're trying to calculate moles of potassium chlorate at the end. And my conversion factor needs to get rid of moles of oxygen and bring in moles of potassium chlorate. According to my balanced equation, I have 3 moles of oxygen for 2 moles of potassium chlorate. So my oxygen goes on the bottom, my potassium chlorate goes on the top, and that way my units cancel, as you see here. The final step is to do the math. So we're going to do 9 times 2 divided by 3. And we'll get 6 moles of potassium chlorate. Here is where you will have benefited if, with our simpler unit conversions, you were consistent about using your units. It's very important to include the substance that you're measuring so that you can keep track of whether you're talking about moles of oxygen or moles of potassium chlorate. Let's try another example. How many moles of lithium hydroxide are required to react with 20 moles of carbon dioxide gas? Again, here is the balanced equation. And we need to identify what is our known, which is carbon dioxide, and what is our unknown, which is the lithium hydroxide. Again, we're converting from moles to moles. From moles of one substance to moles of a different substance. This is when you need the mole-mole ratio from the balanced equation. So I start with my known, which is 20 moles of carbon dioxide, and I'm going to end with moles of lithium hydroxide. So my conversion factor needs to get rid of the moles of carbon dioxide and bring in moles of lithium hydroxide for my final answer. Get rid of the moles of carbon dioxide and bring in moles of lithium hydroxide. Where did the numbers come from? They come from the coefficients in the balanced equation. Remember, if there's no coefficient there, the number is 1. If we don't have to write the 1 coefficient, but it is implied. We wouldn't write carbon dioxide at all unless it were involved in the reaction somehow. So 1 mole of carbon dioxide for every 2 moles of lithium hydroxide. I've inserted my conversion factor and I've checked that my units cancel. And so the final step is to do the math. 20 times 2 divided by 1 gives me 40 moles of lithium hydroxide. As always, sig figs are important. I have 1 sig fig times 1 sig fig, so my final answer should have 1 sig fig. How many moles of nitrogen trihydride can be produced from 4.2 moles of nitrogen gas and excess hydrogen gas in a synthesis reaction? Now, this is one that I expect you to be able to create the equation for. So take a moment to pause the video and write the equation for yourself. You should have come up with this balanced equation. Now let's identify our known and our unknown. My number value that I'm given is for nitrogen gas, 4.2 moles of the nitrogen gas. And I want to know how many moles of nitrogen trihydride. How many moles here? So we start with our known value, 4.2 moles of nitrogen gas. And I think about what conversion factor I need to get to moles of nitrogen trihydride. I want to get rid of moles of nitrogen gas and bring in moles of nitrogen trihydride. And to do that, I need those numbers from my balanced equation. 1 mole of nitrogen, 2 moles of nitrogen trihydride. 4.2 times 2 divided by 1 is 8.4 moles of nitrogen trihydride. Now, in case you're wondering, I should have said this before, in case you're wondering why this value or this value don't limit the number of significant figures. These mole ratios are like counting numbers. They have infinite sig figs. Because this is the perfectly balanced equation, this number can have as many sig figs as I need it to. It's not just the number 2, it's like 2.000000 with as many zeros as I need it to have. It has infinite sig figs. So typically, the number that limits your sig figs for your answer is the number of sig figs in your starting value. Let's do one more example. When carbon dioxide is formed from carbon monoxide and oxygen, how many moles of carbon monoxide are needed to react completely with 3.5 moles of oxygen gas? Pause the video to write the balanced equation. Hopefully this is the equation you ended up with. And now we need to identify what's our known, what's our unknown. We know we've got 3.5 moles of oxygen gas, 3.5 moles, and we end with, we want to know how many moles of carbon monoxide. Carbon monoxide, that's this one. We want to know how many moles of that carbon monoxide we need. So we set up the equation. We start with our known. We're going to need 1 conversion factor to convert from oxygen to moles of carbon monoxide so that we can get our final answer of moles of carbon monoxide. Using the conversion factor from this balanced equation, I have 1 mole of oxygen for every 2 moles of carbon monoxide. And doing the math, we have 3.5 times 2 divided by 1. If you put this into your calculator will give you just the answer 7. But I want my final answer to have 2 sig figs. So I'm going to type in 7.0 moles of carbon monoxide. One thing that I want to point out to you is that I find it very helpful to write my known and my unknown underneath the substances themselves in the balanced chemical equation. That way I can be sure that I'm writing the correct values for the coefficients in the mole ratio in the right places. When I look for how many moles of oxygen I have, I've already drawn my attention to it by writing the value of my known underneath it. So I know I'm looking at this location and this location. And I don't accidentally get confused by looking over here. So I do recommend setting up your problem in that way. I hope this helped.